In section 4.5, we're going to look at the hypergeometric distribution. The hypergeometric distribution is the only distribution you will not be able to do on your calculator, but you can do it in Excel, and there is a formula for the hypergeometric. There are 5 characteristics of a hypergeometric experiment. First of all, you're going to take samples from 2 groups. 2, you are concerned with a group of interest called the first group. You sample without replacement from the combined groups. For example, you want to choose a softball team from a combined group of 11 men and 13 women, so there are 24 people total. A team consists of 10 players. Each pick is not independent since sampling is without replacement. You don't want to pick the same person twice. In the softball example, the probability of picking a woman first is there are 13 women out of 24 total, so it would be 13 out of 24, 13 divided by 24. The probability of picking a man second would be 11 out of 23. Your sample space has been reduced because you've picked one person, they're no longer in the sample. So now the total number of outcomes is 23, not 24. If a woman is picked first, it is 10 out of 23 if a man is picked first. So the probability of the second pick depends on what happens in the first pick. And you're not dealing with Bernoulli trials. This is not a random experiment where you get a success or a failure. The outcomes of a hypergeometric experiment fit a hypergeometric probability distribution. The random variable is X is the number of items from the group of interest. The notation for the hypergeometric distribution is capital H. So we say X is a random variable with a hypergeometric distribution. The parameters for the hypergeometric distribution are called R, B, and N. R is the size of the group of interest, the first group. B is the size of the second group, and N is the size of the chosen sample. For example, you have a candy dish that contains 100 jelly beans and 80 gumdrops. You randomly pick 50 candies from this candy dish. What's the probability that exactly 35 of the 50 candies you pick are gumdrops? So this is hypergeometric because there are 2 groups that you're picking from. The 2 groups are jelly beans and gumdrops. Since the probability that you're interested in is the probability of gumdrops, the first group, the group of interest, is gumdrops. So the size of this group of interest, gumdrops, is 80. There are 80 gumdrops in this dish. The size of the second group would be the size or the number of jelly beans. So that would be 100. The sample that you're picking from this candy dish is 50. So X would be the number of gumdrops in this sample of 50. So when you pull these 50 candies out of the candy dish, how many of those would be gumdrops? So X could take on the value of 0 through 50. So none of the candies you chose in the sample of 50 could be gumdrops, up to all of them could be gumdrops. So how would you write the probability statement that we asked in the first paragraph mathematically? What is the probability that 35 of the 50 are gumdrops? So the way we write that is, what is the probability that our random variable value is exactly 35? Now, how do we calculate this? Well, we need some information before we can calculate this. To be able to put this in Excel, we need 5 pieces of information. All right, so here is a screenshot of the dialog box that you get in Excel when you use a hypergeometric distribution. And we'll go to Excel in just a second and actually put this in. So when you go to Excel and you go to the hypergeometric distribution in the statistic formulas, this dialog box, the first thing it asks you for is the sample underscore S. And this is the probability that it's the value that you're interested in. So it would be that I'm interested in 35 of these 50 being gumdrops. So the first value that you put in Excel, the sample underscore S, is X, and that is 35. So sample underscore S is X. The second number that you have to put in Excel is called number underscore sample, and that is the size of the sample that you pick. Now, in this candy dish that has 180 candies in it, you're going to pick 50. So number underscore sample is 50. So number underscore sample is N. The next number you're going to put in is population underscore S, and that is the number of gumdrops you have in this candy dish. So it is the number you have of the first group that you're interested in. So that would be 80. It's equal to R, and that is 80. There are 80 gumdrops in this candy dish. And then the number underscore population is the total number in the two groups combined. So in my candy dish, I actually have 180 pieces of candy. And the last thing that you want to type into Excel in the last field is whether or not this is a cumulative probability or not. So you're going to type in either true or false. If you're not calculating a cumulative probability, you're going to type in false. And we are not, because we are interested in the probability that if I choose 50 candies randomly from this candy dish, that exactly 35 of them are gumdrops. I think the probability is going to be rather small. So we're interested in X equals 35. That is not a cumulative probability. I am going to open Excel. And I'm going to type in here somewhere what I'm trying to find. So what I'm trying to find is the probability that X equals 35. Okay, I'm going to just move over to the field to the right of that. And now I'm going to input my hypergeometric distribution. So in the top menu in Excel, you have the formulas menu. And that's the menu that I am interested in. So I'm going to go to formulas, more functions, statistical. And then I'm just going to scroll through here till I find something that looks like hypergeometric. And there it is, hypgeom.dist. That's what I'm interested in. And when I click on that, it is going to bring up the dialog box. So again, the first field in this dialog box is the value that I am letting my random, how do I put this? It's the X value, the value of my random variable. So I'm interested in the probability that 35 of these 50 candies are gumdrops. So that number is 35. Okay, I'm going to use my mouse and I'm going to go to the next field down. And now it says number underscore sample. And remember, this is the number in the sample that I pick. So I chose 50 candies randomly, so that number is 50. I'm going to go to the next dialog box, and you might notice up here in the formula field, it's filling out this information. We're doing a hypergeometric distribution. The first two numbers are 35 and 50. The third number, the population, is the number of items in the group of interest, and I had 80 gumdrops. The next number is the total number of things that I have. I had 100 jelly beans and 80 gumdrops, so I had 180 candies total. And then I'm not interested in a cumulative probability, so I'm going to type in false. And as soon as I type in false, you can see down here at the right here, it actually calculates the probability for me. So the probability is 1.436 times 10 to the minus 5. That's what that E minus 0.5 means. That is scientific notation. So this is 1.436 times 10 to the minus 5. I'm going to click OK. And if I'm not crazy about scientific notation, I can make that a decimal. If I right-click on that field, I'm going to go down to Format Cells. So right-click, Format Cells. I'm going to change that to a number to 10 decimal places. So I'm going to type in 10. I could use my arrow and just arrow up to 10, and then OK. And so the probability that X is 35 is 0.00001436. And we kind of suspected it was going to be a small number. I mean, can you think how small it would be if you pull 50 candies from a candy jar that exactly 35 of those are gumdrops? Now, there is a formula that you can also use. And again, this is a formula that only works when your random variable takes on an exact value, and it uses combinations. So this notation here is for a combination. So in our example, the size of the group of interest, we had 80 candies that were gumdrops. In the second group, there were 100 jelly beans, and our sample size was 50. So we can actually fill out this formula. So it's the combination of picking, what did we have? X is 35. How many different ways can I choose 35 items from the 80? So this is how many different ways can I pick 35 gumdrops from 80 gumdrops in my candy dish. And the second combination, B, is the number of jelly beans that I have. And N minus X would be 15. So if 35 of them are gumdrops, the other 15 out of the 50 would be jelly beans. So how many different ways can I choose 15 jelly beans from the 100 that are in the jelly dish? Then we're going to divide that by the combination. How many different ways can I choose the 50 items from the 180 items in the candy dish total? And these three things in parentheses are all combinations. And you have a combination button on your calculator. So I'm going to go over and show you where that is and how you can do this calculation on your calculator. I don't know that it's actually easier on your calculator. I'm positive that Excel is easier to do. But it is one way you can do it if you don't have Excel handy. Okay, so your combination is in your math menu. So over here on the left, and it's in the probability menu. So the fourth menu to the right. And combination is number 3. So what you do to use this item in this menu is N is the top number in those parentheses, and R is the bottom number. So if we wanted the combination of how many different ways I can pull 35 items from 80, then I would type in 80, come here, find the combination, put that in, and then type 35. So that's what I'm going to do. So I'm going to exit out of here, and I'm going to use my fraction button also, because that's going to help me in this calculation. And I can find that by clicking alpha, y equals, number 1 is my fraction. Okay, so my first item in the numerator is the combination of picking 35 items from 80. So the number of ways I can get 35 gumdrops out of the 80 gumdrops in the candy dish. So I'm going to type 80. Then I'm going to go find my combination, math, probability, number 3. And then I'm going to type 35. All right, then I'm going to arrow out of there. And I'm going to put in the second combination. And that was how many ways I could get a jelly bean. So there were 15 jelly beans in the sample out of 100 jelly beans in the candy dish. So I'm going to type 100. Then I'm going to go to my combination, number 3. And the second number in that combination is 15. And I probably should have put a times in between those. Let's see if it works without me putting the times. I should have put a multiplication in there. Let's see if it works. Okay, so in the bottom, it was the combination of picking the 50 items in the sample out of the 180 pieces of candy in the candy dish total. So I'm going to type 180. Go find my combination, number 3, and that's 50. And it worked. It didn't need the multiplication symbol. Isn't it nice that my calculator understands what I'm doing? Thank goodness it understands. So it's the same probability that I got from Excel, 0.00001436. 1.436 times 10 to the minus 5. All right, so let's look at this example. A school site committee is to be chosen randomly from 6 men and 5 women. If the committee consists of 4 people chosen randomly, what is the probability that 2 of them are men? How many men would you expect to be on the committee? So as soon as I see that, how many would you expect, I know I'm going to have to find a mean. So our random variable X is the number of men on this committee of 4. And men are our group of interest. They're the first group because we're interested in finding the probability that on this committee of 4, exactly 2 are men. So X can take on the values that you could have no men on this committee. You could have 1, you could have 2, you could have 3, or you could have 4. The group that I'm interested in is the number of men, and there are 6. So R is 6. The other group that we're looking at is women. There are 5 women, so B is 5. N is 4. Our committee size is 4 people. So this is a hypergeometric distribution where we're interested in a group of 6 and 5 and how many ways we can pull 4. So what's the probability that X is exactly 2? Using Excel, my sample size is 2. My sample underscore S is 2. That is the value of my random variable. That is not my sample size. I know I said that, but that is not correct. That is the value that my random variable takes on. So we're interested in this committee of 4. What's the probability that exactly 2 of them are men? So the number underscore sample is the size of our sample. So in this case, it would be the size of our committee. So that would be 4. The population underscore S is the number in the group that we're interested in. Since we're interested in the probability of getting exactly 2 men, that would be 6. There are 6 men to choose from. The number underscore population is the total. That's 11. There are 6 men and 5 women, and it's not going to be cumulative because we're interested in the probability that X is exactly. I'm going to run back over to Excel, and we're interested in finding the probability that X is equal to 2. So this is, I'm going to go to the field to the right, and we're going to go to our formulas, more functions, statistical, and find hypergeometric. Okay, so we're interested in what's the probability that exactly 2 members of this committee of 4 are men. So 2 out of the 4 are men. We have 6 men to choose from out of 11. And it's not cumulative. So the probability that I choose exactly 2 men is 0.454545. The last distribution we're going to look at is the Poisson. And you use the Poisson distribution when you're interested in, or when you're told that on average you get this many. So if you say, what's the example they use? On average, there are 5 misspelled words in 100 pages in a book. So if you're told that on average this occurs, it's going to be a Poisson distribution. So there are 2 characteristics of the Poisson. The first characteristic of the Poisson is that the Poisson probability distribution gives the probability of a number of events occurring in a fixed interval of time or space if these events happen with a known average rate. So if you see in your problem that you're given a known average rate, you know it's going to be Poisson and independent of the time since the last event. For example, a book editor might be interested in the number of words spelled incorrectly in a particular book. It might be that on average, there are 5 words spelled incorrectly in 100 pages. So the interval is 100 pages. The Poisson distribution may be used to approximate the binomial if the probability of success is small and the number of trials is large. And it says you're going to verify this relationship, and I don't think that we actually give you that homework problem. Maybe we do, maybe we don't. I can't remember. So the random variable X is the number of occurrences in the interval of interest. So for example, the average number of loaves of bread put on a shelf in a bakery in a half-hour period is 12. So every half hour, on average, they put 12 loaves of bread on the shelf. Of interest is the number of loaves of bread put on the shelf in 5 minutes. The time interval of interest is 5 minutes. What's the probability that the number of loaves selected randomly put on the shelf in 5 minutes is 3? So how do you figure this out? Well, how do you know that this is Poisson? Well, you know this is Poisson because you're given an average number of loaves. And when you see that, you know that this is going to be a Poisson. There's no success failure here. There's no two groups to look at. So this is going to be Poisson. And this is our random variable is going to be the number of loaves. And we're interested in this time interval of 5 minutes. So we're given the average in 30 minutes. What we're interested in is the average in 5 minutes. So what we're told is that in a half an hour, we put up 12 loaves of bread. So what you're given is that in a 30-minute period, there are 12 loaves of bread. So we could just reduce this by dividing out a 6, and we could see it conveniently that in a 5-minute period, 2 loaves of bread are put on the shelf. So in this Poisson distribution, since we're interested in this 5-minute period, then we can just take that average that was given to us and figure out how many loaves of bread are put up in the 5 minutes. So what are we interested in there? Well, now it says, okay, if 2 loaves are put up on the shelf in a 5-minute period, what's the probability that you get exactly 3? What's that probability? And how do I figure that out? Well, I'm going to use a Poisson distribution. So let's talk about Leah for a minute. So Leah's answering machine receives about 6 telephone calls between 8 a.m. and 10 a.m. So in a 2-hour period, she gets 6 phone calls. What is the probability that Leah receives more than one call in the next 15 minutes? So X, the random variable, would be the number of calls that Leah receives in 15 minutes. So the interval of interest is 15 minutes or a quarter of an hour. So what values can this random variable take on? Well, it can take on any values from 0 to whatever. So if she receives on average 6 telephone calls in 2 hours, how many phone calls does she receive in a 15-minute period? Well, there's a couple of different ways that you could look at this. I'm not too keen on the way that they do it. I'm more inclined to do it using unit analysis. So on average, she receives 6 calls in a 2-hour time span, which is 3 calls per hour. And I know in 1 hour, there are 4 15-minute periods. 1 hour is 60 minutes. That's 4 15-minute periods. So just using a little unit analysis, in 1 hour, there are 4 15-minute periods. So if I then, the hours divide out, so I can see now how many calls I get in 15 minutes. I get 3/4 of a call in 15 minutes, or 0.75 calls in a 15-minute period. So this is Poisson because only information we have is that the average is 0.75 calls in 15 minutes. So the random variable is a Poisson distribution with this thing here, 0.75. And this thing we call, this 0.75, we call that lambda. So that is the Greek letter lambda. So this average And the time period that you're interested in is called lambda. So in our case, lambda is 0.75. So what are we interested in? What's the probability that there's more than one call in the next 15 minutes? So more than one, is that greater than? What's the probability that X is greater than 1? So we need to figure out, using the Poisson distribution in our calculator, how we calculate X is greater than 1. So again, this is a probability, a discrete probability distribution. So if we want to find X is greater than 1, then we're going to take the probability that X is less than or equal to 1 and subtract that from 1. And your calculator can calculate the Poisson probability distribution of X is less than or equal to 1. And the only two pieces of information that you need for your calculator is the value of the random variable. So we need the 1 and you need lambda. So I'm going to go to my calculator and I'm going to go back to my distributions. And I think as we were scrolling through these in the other videos, we probably saw the Poisson. So again, you got two Poisson distributions, Poisson PDF and Poisson CDF. The PDF is not cumulative, the CDF is, so we are interested in the Poisson CDF. So what we're going to do, I'm going to get out of here, and we're going to take 1 minus, we're going to go back to our distributions, the Poisson CDF, and now we're going to put in our values. So our here it's called mu, that's going to be 0.75. Our X value was 1. So we're going to take 1 and we're going to subtract the Poisson CDF 0.751. And we get 0.173358. So the probability that she gets more than one call in the next 15 minutes is 0.17335. Okay, so let's look at some other examples. According to Baden, an email management company, an email user gets on average 147 emails per day. Wow. Let X be the number of emails an email user receives per day. The discrete random variable X takes on the values 0, 1, 2, 3, etc., etc., etc. The random variable X has a Poisson distribution, and we know this because they give us this average 147. So the mean is 147 emails. What's the probability that an email user receives exactly 160 emails a day? What's the probability that an email user receives at most 160 emails a day? What's the standard deviation? So what's the probability that an email user receives exactly 160 emails? So this is the probability that X equals 160. So we would use the Poisson PDF in this case. And the only two numbers I need to put in here is the 147, which is the average number we get a day, and the 160, the value of our random variable. So let's just do that real quick on our calculator so we can remind ourselves where to find this. So we're going to go to our distribution menu, find Poisson PDF. We're going to type in average of 147 emails a day. What's the probability that I get exactly 160 if on average you get 147? Paste that back into our home screen and we get 0.0103. Point 0.0103. 0.01803. Okay, now what's the probability that I receive at most? Remember, at most means less than or equal to. So what's the probability that X takes on a value less than or equal to 160? So that would be a Poisson CDF, 147, 160. So the only difference in the two calculations is which Poisson distribution you use. And here we get 0.866. And then how do you find the standard deviation? For a Poisson distribution, the standard deviation is given by the square root of whatever the mean that they give you. So they tell me on average there's 147 emails a day. So the standard deviation is the square root of 147, which is approximately 12.1244. And that ends chapter 4.